academic. So we are going to solve a problem today. Yes, this is an assignment on physics 351. That's electromagnetism. It's a course offered by all 100 level students in higher institution. So we are going to dive in already. It's a very simple assignment. So students have been meeting me to help them solve this. So I decided to do it and record it on the YouTube so that at any point in time they can actually come and get it for their own good. So we are going to dive in already. Yeah, we're going to dive in. All right. So here it says derive the magnetic field near a straight line carrying current I. Now this is an example. It's a question on Biot Savart Law. And what's Biot Savart Law? Biot Savart Law states that the magnetic field due to a current carrying current at a distance point is inversely proportional to the square of the distance between the conductor and point, and the magnetic field is directly proportional to the length of the conductor carrying current flowing in the conductor. I know it sounds a little bit complicated, but mathematically, the Savart law, dB, that's the magnetic field, is given by this all over 4 pi I dl sine theta all over r square. That's the integral of this Biot Savart law mathematical expression. You know that this is the permittivity of free space. 4 pi, I is the current, the L is the element of length, and we have here r is the distance from the magnetic field to the conductor, and the sine, of course, is the angle between them. So I'm just trying to rephrase where it's coming from so that if you want to go and make some references and you want to study more on it, you actually know where you are headed to or what you are going to do. Okay, so let's move on here. Okay, so it says here, so let's move on. So you see, derive the magnetic field near a straight line carrying current, Now we are going to use Biot Savart law in solving it. Why? Because I've already stated Biot Savart law, what it is used for, and why we are going to use it. So it's going to make more sense. Why? Biot Savart law is an equation that gives the magnetic field produced due to a current carrying current. It's a law. It's an equation, that gives a magnetic field produced due to a current carrying current. And of course, we all know the right hand rule that states that if a current carrying conductor is grabbed with the right hand, that the thumb is in the direction of the current while the other fingers are in the direction of the magnetic field. That tells us the direction of the current and the magnetic field. It's quite simple. You can see that. Okay, so let's just dive in already. Let's dive in. So from the diagram here given in the assignment, this is the conductor. It's carrying current here, and this is the little elemental length, small element we are considering here. So let me take the camera down so that's the small element we are considering there. So from here it goes, okay, from the assignment given we are having here. So yes, of course, this is our y. So this is the direction of the current. It's going like the current is going. This is our y axis, and this is our x axis. So from here we can draw a straight line from the elements. So here is the L. This is small fraction of the conductor we are considering. That's a little fraction of the conductor what we are considering here. So if you now draw your line here from here to here, we've already gotten a triangle already. Remember, we are using Biot Savart law in solving this problem. So from here we know that here is the arrow, of course. And here's the point P. Let's say this is where we are considering the magnetic field from this point. So we want to find the magnetic field around this point, because they say that derive the magnetic field near a straight line wire carrying current. The relative field at this point, what we are going to consider, this is our y-axis, this is our x-axis, this is the point we have to find the magnetic field. You can write here the B, and down here is our R, that's the distance. Okay, so let's dive in. What do we do from here? You know that I actually told you that we are using Biot Savart Law. So from here, the magnetic field strength, come down here, the magnetic field strength, dB, is equal to the integral of this all over 4 pi I dl, that's the element. I will explain it all over r squared. Yes, so we are making progress over here. All over r squared sine theta. Good. We are making progress over here. All right, so I believe you can see this. Yeah, let me take it down so that you take your time and check it. This is what we've done. The magnetic field is given by this. That's from the Biot Savart Law. So this is the Biot Savart Law. So now, I've been said that already. It's supposed to be an arrow. This arrow is a unit vector pointing in the direction. It's always found from this point. It's pointing in the direction of where the magnetic field is being located at. So we've done with this. So let's now progress. From here. Okay, so this the Biot Savart Law. We want to use it to derive the magnetic field near a straight line carrying current I. I've stated it. I believe you can see it. Okay, so the magnitude of the magnetic field is equal to permissivity of free space 4 pi. These are all constants. I, the current, the L all over r squared. I've already stated the magnetic Biot Savart Law. This. Okay. So the L is in the direction. Of the y. Okay, it's in the y direction. Sorry, it's in the y direction. So from here we're making progress already. Okay, so from here we know that from Pythagoras theory, our r is always given by s squared plus y squared, which is equal to our r will be equal to the square root of s squared plus y squared. This is normal. This is a basic understanding from what we've known in Pythagoras theorem. So that's what we get from that. And also we know that sine theta from here, let's check it. This is the angle. Sorry, this is the angle. Now the angle is facing here, and this is the hypotenuse, right? So we know that from SOHCAHTOA, that's Pythagoras, that's basic trigonometric. From basic, that we know that where the angle is facing is the opposite, and the longest part is the what? Is the hypotenuse. So what will be sine? Sine is what? Sine is opposite all over hypotenuse. So from here, you know that our opposite is x, and the hypotenuse is what? R. So we come here, sin theta will be equal to opposite is x, hypotenuse is what? R. So we are done with that. We are making progress here. From that diagram being given that we should solve. So we are going to input in everything inside the equation and then start solving. I believe you can see that. So we want to put everything now. We want to substitute equation this and this into the original equation. What did I say? Okay, let me say this equation. Okay. This equation 1. This equation 2. Let me take this equation 3. Sorry, I'm gonna list them out so that it will make more sense. Now substituting, putting equation 2 and 3 into 1. putting equation 2 and 3 into 1, what do we have? Now, if we now put this, we are going to have B, that's the magnetic field, will be equal to, we're going to have the integral 4 pi, the current dl, okay, and then the, you know that the sign, you know that what is sign? X all over r, we have x all over r divided by, what do we have down here? Our here was r squared from the original equation was r squared, but here another, given that r itself is given by this, so if you square it all, what are we going to have? We are going to have x squared plus y squared all over this. That's your squaring, that's your finding the cube root. Sorry. We are going to have this. Sorry, let me take it gently. I'm being faster, so I'm going to cancel it and tell you how we got here. So our B here, we're supposed to have the integral of this all over 4 pi I dl x all over r cube. Why? Because it's supposed to be all over r, right? The r comes down from this. Here is x all over r, so that r comes down, it makes this one cube. Okay, so let's progress. I'm gonna push this away and bring the next one in. Okay, where did we stop? Okay, this is where we stop, right? We stopped here. All right, so let's make progress from here. So from here, what are we going to have? Our magnetic field B will now be equal to the integral of this 4 pi I dl x all over, if you now put the value of r, we are going to have x squared plus y squared all over 3 all over 2. That's the cube root of this, all squared. Right? If you check very, very well, what do we have our r here? Is here. And now this becomes cube. And there's already squared here. So this is the same thing. You can either write cube root or this. So it's the same thing. We've not done anything complicated or abstract here. We've not done that yet. Okay, so let's make progress. Now, let's say, let the L equals to dy. That's the element here. Since it's on the y-axis, we make it dy so that we can be able to integrate. So we are saying let the L be equal to dy so that we can be able to find the integral of this function. So our B will be equal to this 4 pi ix all over x squared plus y squared all over 2 dy. So now we now know that we are going to integrate with respect to y. So let's go on. So now we are going to move out the constant outside of the integral and integrate the variables. So our B, the magnetic field, will be equal to, this is a constant. Of course, the current is a constant in this part. I is a constant, and the x also, bring it out because we're not dealing with the x here. Find the integral from minus infinity of the length. In the length, we're not given a specific location where the length is stopping. So we have to integrate from minus infinity to what? To infinity, to positive infinity. So when we do this, we are going to have dy as equal to x squared plus y squared 3 all over 2. Yes. Okay. We're making progress. I believe it's making sense. It's making sense. It's making sense, right? Okay. All right. So let's move on. 3 all over 2. So from here, what do we do? From our basic integral, if you have not watched my videos on differentiation, please go and start with that. I'll soon enter integration. I will explain everything in that class. So for now, I'm just going to go through and tell you what we are going to have using integration. From integration, one of the integration properties, this we are going to have it to integral from 0 Yeah, so you're going to put here 2 because if you multiply this, it will give you 0 to positive infinity dy. It's just a mathematical manipulation. X, you have 3 all over 2. So don't get confused. It's just a mathematical manipulation. It's in integration. Integration has some principle. It has some breakdown and properties. So we just manipulated it in using one of it here. So don't get yourself confused and fixed up over there. So from here, before they finish, now let us integrate. When we now integrate this, we are going to have this all over 4 pi. Of course, these 2 enters here. So where will become 2 pi into have dy all over x squared and there we go. We've done our integration. As I said earlier, if you want to take time to integrate and break this, you are going to spend longer time in this assignment. So I'll leave that up to you to go and revise how to integrate this, and you come up with what we have just had here. You will see that the answer will just be something of this nature. So I'll leave that up to you. If you take much time, if you want to break it up down. So what do we do from here? We take out the x out. So we are going to have this I all over 2 pi x squared. So there was already x here already. Sorry, please include that. There was already x here. The y all over x squared plus y squared 3 all over 2. From 0 to infinity. All right. So from here, what do? We are going to do some mathematical manipulation also from here. See little stuff we are going to add in again to get our desired result. This I all over 2 pi x, because if this and this cancel, we are going to have only one x down. So we are going to do this. Okay, we're going to say y times 1 all over y. We are going to multiply both the numerator and the denominator by the reciprocal of y by 1 over y. So we are going to have here also the square root of x squared plus y squared times 1 over y minus 0 squared x squared plus 0. Okay. Now, as y turns to infinity in this place, you're going to have something different. Also, in this other side, as y turns to infinity, you're also going to have something different. So, if y turns to infinity here, of course, what do we have here? We are going to have this I all over 2 pi x to have 1 all over square root 1 over I squared in bracket times x squared plus y squared. Sorry, it will look a bit as if it's too complex, but I'm telling you, trust me, it's not complex. It's just for the fact that I'm just trying to break down using calculus integration. That's why it looks this way. But trust me, if you understand integration, you find this thing very, very simple, because all what we're just doing is just integration, finding the integral, and some basic stuff we are doing here. So from here, what do? We now say here will be equal to this pi half all over 2 pi x 1 all over the square root of x squared all over y squared, right? Because here becomes 0, right? So when you put this together plus 0, here becomes 0 already. So in this place, what are we going to have from here? When everything here becomes to infinity, of course, when you now substitute everything here to become infinity in this place, here all becomes 1. Everything all become 1. So what do we have? Well, we're really going to, Okay, so sorry for the breakdown. Now, if you now look here, if you multiply this by this, it gives us y squared all over, so x squared over y squared, of which if you put in infinity here becomes what? 0, that's 1, 0, and then here the same thing. Okay, let me break down here. So here supposed to be this x squared all over y squared plus, supposed to be plus 1 all over y squared all over y squared. Here becomes 1, right? And here, if now put in 0, here all cancels out. And now we're left with 1 all over 1, which is equals to 1. If you now multiply everything here, we will now have the percentage of this all over I all over 2 pi x. So here becomes our answer. Now, if you check carefully from what we've done from the beginning here, you don't agree with me that the magnetic field near a straight line while using Biot Savart law is given by this. I know you all are familiar with the one using Ampere's law, but the mathematical expression using Biot Savart law is expressed by just this. What we've just done here is all is being expressed as, that's it. You can see it there. You can see it clearly there. There we go. So take your time. Just integration. What I've just done here is just integration, integration, and integration. So this is what we have here. You have this over x. All right. So from here, if you now since we know that we're dealing with the distance being r, so that's when you can change the x to become r. So our b will now be equal to this all over 2 pi r, which becomes the magnetic field near a straight line wire carrying current is given by this from Biot Savart law. So this is the solution to it. I want you to subscribe to the channel, share this video, and also comment, like, ask questions below the comment section. We always be here to give you answers, solutions. You can also follow us on our Facebook page at Explicit Physics Academic, our Instagram at Explicit Physics Academic. We're also on WhatsApp. You can dial this number, not dial, sorry, you can message this number only for messaging only. +234 811 318968. I see you next on the next video. Thank you. Bye.